All attendees are in listen-only mode.
Good morning, everyone. My name is Tracy Reddick, and welcome to American Iron and Steel Institute's launch webinar of the Geometrical Analysis of Sections GAS 2.0. At this time, I'd like to introduce John Catterall, Vice President, Automotive Program for AISI. John?
Thank you, Tracy. Now the GAS software is a Windows-based user-friendly first-order analysis tool for the analysis of steel sections. It takes into account buckling, and the team has done a great job of updating the software, and you'll see that as we go through the webinar. I'd like to introduce presenter Dr. Don E. Malin, Lecturer of Integrated Systems and Design at the University of Michigan. Don will be walking us through the new release of the software, again, which applies to thin wall section for automotive design. As mentioned, Don is a lecturer at the University of Michigan, Ann Arbor, where he teaches graduate courses in product design and automotive body structure. Don is also the author of the textbook Fundamentals of Automotive Body Structure Design. Prior to his teaching activities, he was an engineering executive at General Motors, where his last assignment was director of GM Innovation Zone. I actually worked with Don at General Motors for a short while. His PhD in mechanical engineering and industrial and operation engineering is from the University of Michigan. And now you will hear from Don and the launch of AISI's Geometric Analysis of Sections, GAS 2.0 software. Don?
Well, thanks a lot, John. I'm really excited to go through this new software with you. It's quite an improvement over GAS 1.0. And I want to just emphasize that what we're talking about here is really related to thin-walled section design. So before we go into the details, I want to kind of go through the thought process of why this software is so important. We know that tall, thin wall sections are very mass efficient. That's why we use them in auto design. However, they bring along an additional failure mode beyond just yield. And that failure mode is plate buckling of the little plates that make up the section. And unfortunately, the classical section analysis doesn't really take into account this plate buckling. And that was the whole purpose behind GAS 2.0. And again, it's a Windows application. The purpose is to estimate the strength of these thin wall sections where the plate buckling is present. So the theoretical basics for GAS is quite sound, and it's kind of been well established over the years. What we're trying to do are two things. One is to estimate when the plate buckling would occur. What's the stress level? What's the load level on the section? And then secondly, we want to estimate the maximum load carrying capacity of that buckle section. And we do that with something called the yield of the effective section. We'll come back to that term again and again. So we're not going to go deeply into the theory, but I do want to show a couple of slides just to establish what we're talking about a little better. So what you see on the slide now is a thin wall section. Just for simplicity, it's a square section, and we're visualizing it as made up of 4 flat plates that are connected at the corners, and we're applying an axial load. If we increase that axial load to some point, we'll get the plates of this section buckling as you see here in this slide. And let's just take a look at one of those plates. We see that sigma CR is the buckling stress. This is the stress where that flat plate will just kind of snap over from being flat to this buckle shape. And that depends on both the thickness and the width. And here we're looking at this as a steel plate. And the boundary conditions here along the edges are simply supported around that plate. And here's what theory tells us about the relationship of this buckling stress to the thickness and the width. So on this chart, we're plotting on the y-axis the plate buckling stress sigma CR. When will that buckle shape occur? And it turns out that that is related to the width to thickness ratio, the B over T ratio. So on the right side of this chart, we have plates that are very, very thin and wide. On the left side, we have really stocky, thick plates. So we can kind of see that for thin plates, we have a very, very low buckling stress. And as the plate gets much more stocky, it takes much more stress to go into that condition. And just note here that that stress is proportional to the B over T ratio squared. So it's quite sensitive to that. So this is the behavior of a buckle plate. Let's go back and consider the buckling section. But before we do that, let's kind of look at how this kind of plays out in a design problem. So we're going to take that plate, we're going to design it for a material yield stress of 200 megapascals. And it turns out that the buckling stress is equal to 200 megapascals when the B over T ratio is about 60. Okay, so we've designed this plate, we've kind of optimized it for the material, and we've made its dimensions as B over T ratio so that just the buckling stress and the yield stress occur at the same time. But we know we have a wide range of steel grades to choose from. 200 is kind of on the low end of the yield stress for the material. Let's just take this same plate and substitute a grade that has a yield stress of 600. So we see that what will happen is that we'll never really reach that yield stress. We'll buckle before we reach that. Okay, so we're not getting the full benefit of the material. So what we have to do is change the plate proportions. We would have to make it more of a stocky plate in order to achieve that full yield strength potential of 600 megapascals. So this is the idea of GAS. We've been talking about just looking at a single plate. Let's look at a section again. And here's where this idea of the effective section will come in. So here we're again looking at the square beam made up of 4 plates. We're pushing a load on it, a compressive load. We haven't yet reached the yield or the buckling stress. So we push it a little harder, and finally we reach the buckling stress, and the 4 plates buckled. But this isn't the end of the load-bearing capacity of that beam section. We can continue to increase the load until we reach something that we're going to call P ultimate. At this load case, what's happening is that the center of the plates aren't really taking much more stress than when they initially buckled, even though we're pushing harder on it. Where the stress has increased was at the corners. And this ultimate load carrying capability of the beam is defined when we reach yield at the corners of the plate. So you can see this is quite a complex stress distribution. We have a relatively simple section of a square section. You can imagine with something much more complex like a rocker, how difficult this would be to predict. So what is done is we substitute this real condition that we're looking at here with something called the effective section. And you can see that in the effective section, what we've done is thrown away some of the material in the center of the plate, which isn't very highly stressed. And we've put the whole section at a uniform yield stress, sigma y. And the theory tells us how much of this material to throw away. So we're not just doing this arbitrarily. The theory's been well established, and there's also a lot of empirical data that has been used in order to establish that. Okay, so these 2 states of stress give us the same answer for this P ultimate, and this is the ultimate load carrying capacity of that beam, something that we're really interested in body design. And before we go on, I just want to make one point clear. This can be a little bit confusing. There's lots of ways that things can buckle. Whenever we have compressive loads, we have structures that can buckle. You're probably familiar with something called oil or buckling from strength materials days. And if we have a very slender beam that's somewhat long, if we push on that hard enough, we'll get a condition that looks like this. Okay, this is really rarely seen in auto design. Our beams are really never quite this slender or long in order to reach this state. So this is not what we're looking at here. Again, what we're looking at is a plate buckling where these plates are elements of a section, and this is what we're talking about with the GAS 2.0. Okay, so here's how this will play out. We'll kind of take a real design concept. We can model it in GAS. GAS will tell us what the yield of the effective section looks like. So here we see where some of the plates are less than fully effective. We're really not getting the full advantage of that material. Here's a little bit at the top of the flange. GAS will also tell us what is the load at which this state will occur. And then, of course, what we can do is use the software to redesign the section. And here I've just, for example, done a couple of things. I've added a bead here to stabilize this section a little bit, so you see how it's much more effective. And I've added a little flange curl at the top to make that effective. And of course, there's other things we would maybe want to do to this section to make it more fully effective. But one of the important things here is GAS will tell us, well, how much did we improve that section? So this is the whole idea behind GAS. It's the reason to use it. Let's take a look at the user interface. The graphical user interface is very convenient, fairly common today. Let me point out a few important areas. We now have the ability to import a section from a CAD system in either IGES format or STEP format. There's 63 steel grades properties have been preloaded, so you can select from one of those, or the user can enter their own steel grades to use. GAS does two kinds of analysis. One is called a nominal analysis. That's the classical area properties that you're probably very familiar with. It also does something called the effective analysis, which is that yield of the effective section that we're have just been looking at. The results are shown graphically as well as a table of results. We have the ability to construct a section from scratch, or to alter and import a section, or modify a section to improve its performance. We can control the view window that's in this grid area. We have ways of interrogating the model. So if we have some problem with the modeling, we can show line numbers and node numbers and things like that that will help us kind of diagnose and correct a model. So this is the interface. Here's some of the steps in importing a section. Again, we can either construct or import the section like you see here. So this is a section in three-dimensional space right now. GAS will automatically identify the true view and translate the data. We can condition the data, and the GAS model requires a line representing the midpoint of the data. So often we'll import two sides of metals, and the conditioning step will get rid of those two. And this is somewhat automated as well. And then we assign materials, and these are some of the materials in the database. Assign a thickness to the parts. We can position the wells on the section. Minimize the number of lines. This will improve the fidelity of the analysis. And then finally, we have a section that's all ready for analysis. So again, there's two types of analyses. One of them is nominal, and just to give you a feel for what that is, there are things like cross-sectional area, the centroid. That information is also shown graphically. Moments of inertia, section modulus, principal coordinates, and then some torsion properties here as well, the torsional constant. And an interesting one that many systems don't provide is the warping constant for open sections. And then GAS provides the effective properties. That's kind of all of the above, plus the load at which the buckle section will yield, and then the little picture of the effective plates. So one thing we need to specify here is something about the loading on the section. So the yield of the effective section depends on three things. One is the section geometry that we've looked at before. Another is the material yield. So once we specify a material, we have that. But the third is the loading. And why is the loading important? Because loading determines which plates are in compression and may buckle. So what we've been looking at up to now is the axial condition. And the reason that's important is that under axial, any of the plates that make up the section may buckle. Other conditions that we can specify to GAS are bending moments, like you see here. These are bending moments around the x-axis, where the top shows a condition where only the plates on the bottom of the section will buckle because only those are in compression. And then we can have a similar kind of thing with moments around the Y. So we do need to specify the loading. So let's say we're interested in improving the section that we had just looked at before under axial loading. This was the result. So we're looking at a design and we say, well, what do we change in order to increase P ultimate? Let's take a look at some general things that we can do. One is when we look at the relationship between the buckling stress and the width to thickness ratio of the plates. Generally, what we want to do is reduce that width to thickness ratio. So one of the obvious ways to do that is to increase thickness. Unfortunately, that increases mass proportionately, so that's generally not something that we want to do. So kind of what we're looking at is ways to reduce the width of the plates. So here's one way to do that, and we're just looking at, for an example here, a hat section where that bottom plate is the one that we're focusing on. So how can we make that plate width smaller without really changing the whole geometry of the section? Well, one thing that we can do is add a bead. And when we do that, we kind of effectively half the width of that plate. So that will radically improve the B over T ratio. Here are some other ways to do that. So the second case here is we're going to add some corners to the plate in order to reduce B. If we have a flange, we can just add a little curl, and that will change the boundary conditions and make that flange more stable. And then finally, on the right-hand side, if we can change the shape from flat to a crown shape. So let's go back to the example. Here's the ways that we've talked about, and let's look at changing the shape. And what we're going to do is change the shape of that flat area to a crown area. And we can kind of see on the right-hand side, the reason that's going to be important is that that we have an area here that is less than fully effective. So it's a simple change to make in GAS, and we get the results here. So we've kind of made that whole area of the section fully effective now. And the bottom line is that we've improved the ultimate load carrying capability of that section by about 6% with that very simple geometry change. So I think you have a feel for what GAS can do, how it works. One of the things I'd like to end on is kind of thinking about what is the role of GAS in the design process. So here we're looking at a motor compartment mid-rail, and you can see the GAS model on the right. This is under an axial load. We can see the load carrying capability. We can see some of the areas where it might not be fully effective, but we know that we have lots of other tools that we could use to get a similar kind of a result. So finite element analysis is, most definitely in our toolkit. So what we want to talk about a little bit here is, well, what's the role of GAS 2.0, recognizing that we have these other analysis tools. And the way I'd like to talk about this is by taking an example. So here's an example design that already exists, call it alternative A. And let me get the, so here we're looking and focusing on this area here, which we know kind of our longitudinal structure has to snake underneath the occupant's feet, but above the ground clearance line. And here's the proposed design from maybe a product planning group. And what that does is lower the seating package and really takes a lot of space out of that. And so we're confronted with these kinds of situations a lot. And basically, the question is can this section that fits through this space be made to work? And we're going to just take arbitrarily, we're just going to say for the moderate overlap front barrier, the 40% overlap barrier. So how do we attack this problem? It's going to be in the context of the system engineering process. So we have some kind of function at the vehicle system level, but we know that we can flow that function down to what's the function of the body structure in that, of what's the function of the motor compartment, what's the function of that little beam element. We can flow down requirements to that level, and then we can kind of develop performance by comparing performance versus the requirement, and then iterate on that. Okay. And we can do this kind of comparison here at two levels. One is at the very top of the hierarchy, where we make a full model of the whole vehicle, and we can compare that to the requirements, and then are we meeting the requirements? If not, we just kind of iterate around. Okay. This is a very common approach. It tends to take some time. We know that we generally will batch a whole lot of different changes into one model before we run it. So there's a certain amount of time involved before we go from a concept to actual performance data. So what we kind of see as the role of GAS is to supplement this by iterating at the very bottom of the hierarchy. So maybe we take a performance level of the current vehicle and we make a GAS model of it, and then we kind of see how the changes influence that. And we can do this fairly rapidly. Bringing data into GAS, doing a model can be done in just minutes. Within 15 minutes or so, we can go from nothing to a valid model and have some results. And then modifying it is also very quick. So we can make lots of iterations at this very bottom part before we go and start to iterate at the top part of the hierarchy. So the advantages here are speed. It can work with very little math data. We might just have a sketch of a section. That will be fine. We can model that in GAS. You saw from the graphical output of GAS that we can get some intuitive understanding as to why a section might not be performing to the level that we want. And we do recognize we're getting approximate answers here that we definitely need refinement by eventually the full finite element analysis. So here's how we see GAS's role in the design process. So across the top, we're going from product planning all the way through to validation and manufacture. So we see the primary role of GAS as being in the early design stage, where we can ensure that we create initial designs that are more likely to work. We can ensure that we're leaving enough packaging space for efficient structure to be defined later on in the process. And then hopefully this will result in fewer problems to fix later. There is a role of it in the more detailed design stage where we have problems that we need to mitigate. We can identify those and correct them quicker. One of the things we can do in GAS is to screen lots of alternatives sections, and then only model the more promising ones in the more detailed analysis with finite element analysis. So just to summarize, what we've been talking about is this idea of plate buckling analysis of thin wall sections. Why is it important? Really, when we begin to use advanced steel grades with higher yield stress and tensile stress, we really need to understand the geometry of the section and how it influences buckling behavior. So this whole idea of yield of the effective section is a really nice way to visualize what's happening in a section under loads. We see again that it's useful both in the early and detailed design stages. We think it's simple enough that people who might only use it intermittently could still benefit from it. It doesn't take, it's not a big learning curve. So design engineers, CAD operators, as well as analysts could use it. It is, of course, useful on laptops. It's also good on PC tablets, for example, Surface tablets, very portable. You could actually run an analysis right at a meeting, for example. It's that quick and easy, as well as at workstations. So that kind of concludes the main talk that I want to give. I do want to acknowledge the really fine work that was done by ETA. This was a major development project, and we really appreciate their very large contribution. Hisham Azat was the program manager, and we had an advisory team of both OEMs as well as steel suppliers to support the ongoing effort. And I do want to just kind of recognize that there was a GAS 1.0. It goes back way to 1995, which really laid the foundation. We really built upon the theory as well as the user interface with what we have today. So you can obtain a copy of GAS 2.0 at this website. This is where you would click in order to link up with that. Not only is there a free download of the software, but there's a user manual, there's training videos, there's some sample exercises for you to try out. Okay. So with that, I want to thank you for your kind attention. And I understand that Dr. Azat has been kind of watching the questions tab, and we're going to go into the Q&A right now.
Thank you, Don. Good morning, everyone. This is Hisham Azat. I really hope you've benefited a lot from this webinar. It's really a great piece of work that has been done. So I appreciate Don's actually trying to squeeze it in a short period of time. So I will be looking at some of the questions that have been posed. So I do have some technical questions, Don, but before we get into that, there are a couple of housekeeping questions. I know that a lot of people have been asking whether these recordings or this session is going to be recorded and if the presentation is going to be available. The answer to both is yes, and in the same location where you can download the software, you can actually access the webinar recording as well as the presentation material, and as Don indicated, some other training modules as well, which you will find extremely useful and very interesting. There was also a question relative to how can we use, as Don indicated, once you download it, there's an executable file. It just basically run the executable file and install it on your laptop, and you're all set to go. So with that, Don, are you ready for my some of the technical questions?
Yes, all set.
Okay, so the first question is, what kind of material properties are required for this software?
The software only requires the yield stress. That's really the main factor. It requires a modulus of elasticity, but this whole software is based on steel, so that's already preloaded.
Okay. So yeah, to that point, this software is basically based on only steel. So everything is built in with a material library that the software has that includes quite a number of steel grades, including third generation steels as well. So another question, Don, does this software apply only to axial loading conditions?
No, let me, maybe I can go back to a slide here. So all of these loading conditions are supported. So at the top, you see the axial condition that I've used because it's simple and it makes the explanation of the software very easy. But at the bottom, you see the other directions. So we can have moments around the x-axis or the y-axis, and they can be either positive or negative. So it supports all of these conditions.
Very good, thank you. There's another one which is, I think, very interesting. Does the spot weld location on the flange affect the buckling condition? Where the spot weld is positioned on the flange, would it affect the buckling condition?
Yes, most definitely it does. And GAS realizes that, and it predicts the proper results. So for example, if we have a long flange and we put the spot weld kind of at the very bottom of the flange, the buckling stress of that long kind of unsupported piece will tend to buckle at a lower load. Maybe I can just use this slide to draw that. Let's see if I can do that here. So here's a flange, and let's say the rest of the section is down here. So if I put a flange way down here, this flange is a flat plate. The B value is relatively large, so it will tend to buckle at a lower load than if I were to put the flange here, and now that B value is smaller. So that's kind of a neat study that can be done with GAS is actually the influence of the positioning of the weld.
Okay, thanks. I have another question. The light yellow areas, when you showed the effective section, the light yellow areas that you're showing, are these buckled or are they yielded?
Let's use this one to answer that. So, okay, so we see that this is, here's a plate here, and that's the unaffected area. So that if we were to look at the true stress distribution here, let's see if I can draw it. It would look something like this. So the yield stress would be at the corner and would have a much lower stress here in the area that we've thrown away the material. So we're saying that in this condition, all the corners are at yield in this section because it's under an axial load, and something less than that everywhere else.
Okay. I have another question. I guess this is for you and I. Is there an optimization tool within GAS?
This was one of the important areas that we wanted to make sure that we took into account. So here's a little diagram. I thought this was a little bit too much to include in the webinar proper. So this is kind of showing that we have a file system that interfaces with the graphic interface that you look at with the analysis engine doing the calculations with the material file, and that IO can interface with the computer data. But what I wanted to show on this slide is there's the possibility, it hasn't been implemented yet, but there's a possibility that this IO file system can interact with a section optimizer. So we had that in mind. The structure of this file is such that it's very conducive to outputting and inputting from an optimizer, but that isn't integral with GAS 2.0 at this particular time.
Okay. There was a question relative to the welding, and I think you've covered that, but let me go through this. The question is, how do we specify joining, i.e. weld spots, etc., in the section?
Okay, let's see if that's go back to the user interface. Okay, so we would have we would construct a section. Here we're under section here, and here are some tools to create a section. So I could use a line tool, for example, to create a section that looks like that, and another section, another part that looks like this. So I have two parts. There's a weld tool here, and I just specify where do I want the weld. So I would specify a point, and then what do I want to weld it to? And I would just say I want to weld it to that part, and that would give a weld there. So I can specify the location. I can specify what parts are being welded.
Okay. I have a question here that says, can gas be used to design aluminum sections? And I can field that. No, the answer is absolutely not. This is developed with the American Iron and Steel Institute, and the material properties there are not, you cannot be changed. So you cannot use those for aluminum sections. And I had a question for you, Don. In the effective section, there are a lot of approaches. Which one is the software using?
Okay, let's jump out and take a look at an example here. Maybe this slide would be good. Okay, so again, there's a lot more theory that I haven't talked about. There in the presentation there was 3 references given. Those go into a lot of detail, but what the questions are twofold. Well, first of all, what is the value for sigma CR? When will a plate buckle? So if we have a plate of thickness T with B and material properties, at what point will the plate buckle? So that's one point of theory. Those are very classical buckling equations that are given in the 3 references that we just looked at. We'll go back to those just so you see what they are. The other question is, how much of the material do I throw away? That's kind of the other question that we have. So this is the effective width is kind of the sum of a half a width there and a half a width there. There's several different approaches at that. They depend on what is the shape of the stress curve across the plate. There's several different approaches. They all give approximately the same answers. The one that GAS uses is been very well established. Let's go back right to here. Here we go. So there's 3 references here that I would recommend on a question like this. Cold form steel design is a very famous book that goes into this, and we'll tell you about which effective width is used. And I do want to make the point that this isn't just a theoretical effective with. That there's been lots of empirical studies where lots of tests have been done on thin wall structures, and that information is not only in all three of these references, but it's also in the software behind GAS 2.0.
Okay, great. I think that covers also a comment or a question that I see relative to trying to understand a little bit more about the analytical assumptions. So I think that kind of covers that as well. Okay, so another question, Don, is what about torsional loads and shear loads?
Only the cases that we looked at before. So axial bending moments, those are the only ones that are covered.
Okay. There's another question relative to limitations would affect the use of GAS 2.0 for materials other than steel. Any future plans for multi-material versions? The answer to that is basically no. As Don had alluded to, this is basically a newer version of the older version of GAS 1.0 with some user-friendly interface. And again, the software is primarily focused on steel and steel applications. Question for you, Don. Can we track stress at a point in the section for a given load?
Yes, we can. I omitted that from the presentation, but let me just show you what you would see. I can mock it up here, I think. So in this case, we can put the stress distribution. It will kind of show something that looks like this if we had it. So there's a little button in GAS. You can just, it will say, do you want to see the stress distribution? And you just click that and you'll get the curve that looks like this, which in this case, this is an axial loading. So this would be uniform stress all the way around the section. But if it's bending, of course, it tells you something about where the neutral axis is on the section and gives you the varying stress distribution.
Okay, very good. Another question I think we can field, if we would like to add a material to the library, do we need details of the stress strain curve of the material?
No. Basically, all you will need is the yield stress. That's the main parameter that the model uses.
All right, and we have a question here or a comment saying, I guess it is a two-dimensional analysis for the cross-section of the beam. Could we touch a little bit more on the criteria on how to define effective section of plate beam? Perhaps we need a little bit more definition on what is meant by that. So let me move on.
Let me take a quick stab. Just I mean, if we have a beam and let's just use a very artificial case here. Here's a beam that's supported at its ends and loaded in the middle. So it has a bending moment that looks something like this. That's the bending moment diagram. So we have the same section for the whole length of the beam, but we would do the analysis where the moment is the maximum. So we would have to come in with some knowledge of the external loading of the beam, and that's where we would cut our section, where the moment is the greatest.
Okay. All right. A question saying that can this calculate the force to crush the section? For example, on slide 11, can the section be loaded with a force along the x-axis?
Right now, the software does create the the crumpling load of a stub column, it's called. So it's a short, stocky column. It uses a particular analysis, and again, I would encourage you to look at the user manual once you download that, or one of the 3 references. But it does give a rudimentary calculation of that. That's one of the areas that we're looking at improving in the future. There's many models of that average crush load of a column, and the one that's in the software right now is a very basic one.
Okay. Okay. Does the steel properties or the material library include press hardened steels, hot stamped steels properties?
Maybe that's one you can address better, Hashem.
Yes, I believe it does. So yeah, these are included in the material library. And by the way, to the previous question, users can add their own materials as long as they're steel, because you're not going to be able to change the elastic modules. So one of your sections looks like an A-pillar. Can the program look at the loading condition?
It can. Let's go take a look at that. It is an A-pillar. That was a good eye. So let's kind of look at this. So the user has to bring the loading condition to the section. So you have to decide if you're interested in this in a axial loading condition, or maybe a bending loading condition, maybe a kind of roof crush thing. You might be more interested in a bending moment, and then you specify the mode of loading, and then GAS will give you the result under that mode of loading and tell you what the maximum capacity is for that condition.
Okay. How long does a typical simulation computation time take on a single thin wall section?
The actual computation time is virtually instantaneous. It's seconds. The modeling time for this this A-pillar, if we imported this from a CAD model, maybe 5 minutes to come up with a usable model in GAS. And then, of course, the instantaneous solution time, and then modifying it like you see here by putting a slight crown in it, that might take another 5 minutes, just to give you some idea of the cycle time. So it's extremely quick.
Okay. Any options to compute and display the stress distributions within the section? I think you've answered that.
Yes, it
so
does.
for example,
it does do that.
Yeah. Okay. Can you talk? Another question here. Can you say a few words about holes or sections not welded, open sections?
Yeah, they can be analyzed as well. They tend to be very unstable. So if we have let's see if I can draw a section here. Now, if we have just take that as an arbitrary open section. So GAS will compute the nominal properties. Those are the classic area properties. It will calculate the warping constant for a section like this, which is very useful for twisting. If we calculate the effective properties, these very long, unsupported sections will probably cause a failure mode in the computation because they tend to buckle at extremely low loads. But at least the software will give you that information that it's not a very stable section. But it will calculate the nominal properties, and depending on the length of the flanges will often calculate the effective properties unless the B value is much too long.
Okay. There's a comment and probably a question embedded in there. It says curved segments appear to be simplified. Can the point pitch be controlled? I think yes, but you would care to comment, Don?
Yeah, this is an area that I would really recommend one of the training videos for more information on. I think it's training video 2 or 3 for you to get that. We could, for example, oops, let's go back to the marker. So we approximated a kind of a continuous surface with one with just a point. We could have added several more points here to make it geometrically look more the same. However, with this kind of analysis, often we want to minimize the number of lines, and that's because the buckling stability is determined by the number of nodes. So, for example, if we have an arc that is made of 2 points versus one that's made of more, let's see if I can get this to work here. So here we have 3, here we have 4. The 4 points kind of approximates the curve a little better, but this becomes a B value. This becomes a B value. So the more points we add, the smaller the plates and the more stable they are. So there's a judgment call between the how well you want to how much fidelity you want to have in matching the geometry versus how conservative you want to be on the buckling characteristics of the plate. And again, there's more on this in the training video, and I would kind of encourage you to give that a look.
Okay. Does either STP or IGES files work better, more robustly, more consistently? Any comment on that?
Well, we have limited experience with STP files. The IGES we've used work just fine. You're probably all familiar with A2 Mac 1. We've used a lot of their IGES files on sections, and all of them have worked flawlessly. One of the areas that you can save a lot of effort here is when the CAD operator cuts a section, is to have him not include a lot of the background information. So things like weld nuts, just leave those out of the data that's transferred. Otherwise, you have to delete it in GAS, which just adds to the effort there. But they both seem very stable.
Okay. One final question that I see here, and again, it goes back to something that I've already answered, is can it work with mixed metal problem? And just so that we're all clear, this software has been built on steel properties, and it works only for steel sections. So it does not support any other kind of material for that matter. So just to be clear about that. So it won't work for mixed material. Mixed grade, yeah, you can mix any grade you want of steel as long as it's steel. So it will work for that. I don't see any other questions, Don. I do have one question. Maybe it would clarify something. This GAS 2.0 software, does it apply to all structural sections, or is it exclusive to automotive structural sections?
It focuses on thin wall design. So that was the main thrust of GAS 2.0, and that's kind of its niche in the analysis tools. In the thin wall sections kind of tend to buckle. So that's the whole basis for GAS 2.0. So it works with sections, using this idea of the B over T ratio. B over T ratios of 10 or greater.
Okay.
It works if the sections get to be, or the plates get to be very stocky. Maybe like a classical civil engineering I-beam. That would probably, GAS would not be a good tool to analyze something like that.
Okay, very good. Very good. I do not have any more questions. I do have a lot of comments praising AISI and thanking them for the software, and also thanking Don for his presentation. Oops, I got one more. Yes, does this work for stainless steel? E value is usually lower for stainless steel. Well, the answer to that, Don, is I think we can accommodate a slight change in the elastic modulus within a certain range for steels, right?
Yeah, I think generally, we see that GAS is an approximation tool, a good approximation, but like all models, an approximation. So the amount of variability on modulus with different types of steel, I think, is kind of within the margin of error.
Okay, good. All right, with that, I'd like to thank you, Don, for helping us with the this webinar, and of course throughout the development of the software. You have been instrumental in making sure that it's an accurate piece of software. So thank you so much. With that, I'd like to send it back to John Catterall.
Thank you, Hisham. And I want to echo what you mentioned. I want to thank Don for a great presentation, very clear, informative. And again, the development team that worked to update the software, they've done a great job, and hopefully as all of you exercise the software, you will find that fact out. Also, I want to thank everybody that attended today. I was scanning through the list. I know some of you personally, so it's good to see you virtually in these times. Just wanted to all let you know too, we have another seminar set up for next week. On June 25th. We've actually got Stu Brown from formerly General Motors, who's going to be going through our new launch of the steel bumper system version 7. So please feel free to join us for that. And with that, I'd like to wrap everything up and thank everybody for your attendance. Goodbye, everybody.